Hello and welcome back to question 8, applications of integration. In this question, we're supposed to do a substitution to solve an integral that's otherwise unsolvable. Now, to make a substitution, we need to look out for some things, because I know students lose meta marks when they don't do a complete substitution. What do I mean by a complete substitution? So let's take note, the substitution to be made here is x equals to cosine theta. Now, in this integral here, we're going to change a few things. So I want you to watch out. Go from left to right and make sure you hit all three things. Number one, if this integral came with some limits of integration like a to b, make sure you change those values, because a represents a certain x value, b represents a certain x value. If you change to, for example, x equals to cosine theta, I want some values in theta instead. Right? For example, when x equals to a, what is theta equals to? Put that value inside here, and likewise for b. So that's the first thing to watch out for. Right? But in this question, there's no need for this. That's fine. Sweeping over to the next part, this. Okay, this one I think everyone knows what to do. Every time you see an x, replace it with a cosine theta. Okay, I won't elaborate more. Now the last one is this. Right, so make sure you don't forget to substitute out your dx as well. In this case, I want to have something that is in d theta. Now, how do I do this? I will have to differentiate this equation here. Okay, so I'm going to differentiate the equation implicitly without respect to any variable. Differentiating x gives me a dx. Differentiating cosine theta gives me a negative sine theta. Not to forget, I need to integrate the argument, so I get a negative sine theta d theta, which means I'm going to substitute dx with this thing over here. Now I'm ready to do my substitution. Okay, so the integral that I'm provided by this question, no limits of integration, that's fine. We switch over to here, it's exactly the same. Now for the main expression over here, this is changed to this, and finally my dx is substituted with a negative sine theta d theta. That's how you check if you have done a complete substitution. Now, the next part, we can simplify a few things. For example, the denominator actually is just equals to sine theta. And that sine theta will cancel very nicely with this sine theta over here, leaving us with just an integral of negative cosine cube d theta. Now, integral of cosine cube theta is relatively straightforward if you have been practicing your tutorials. If you have not, then the trick actually is to take out a cosine square theta, turn it into 1 minus sine square theta. Right? So it's 1 minus sine square theta times cosine theta. Why do you do this? Because if you expand this out, you're going to get this and this. Both of these terms are, you can integrate them directly. No need for MF26, no need for integration by parts or any trig identity. Just directly integrable. Because this is actually sine cube theta over 3. Think about it, yeah? And this is just sine theta. Okay? So you arrive at this answer. But this is not the final answer, because remember we're solving the integral for x, not theta. So let's do a substitution back to x. Now the problem is, I know x equals to cosine theta. What is sine theta supposed to be? That's where you go back to your secondary tool, trigonometric ratios. You draw a right triangle, you draw a theta and say that, hey, cosine theta equals to x. That means adjacent over hypotenuse should give me x. The simplest way to do this is just to write an x here and write a 1 for a hypotenuse. Right? It's always easier to make the hypotenuse 1. Remember that. Now, sine theta, I will need to know the opposite sides. To get this value here, I used Pythagorean's theorem. Right? Hypotenuse square minus the adjacent square. Then you square it, the whole thing. So sine theta will be this value over 1. Right? So it's always convenient to have the hypotenuse equals to 1. So let's make a substitution back. So from here to here, I actually skipped one step. So let me explain what I did first. I actually factor out a sine theta. So this becomes sine square theta over 3, and this is minus 1. So I factor out a sine theta. This is sine square theta over 3 minus 1. Okay, and then combining this into a single fraction, you actually get a negative 2 negative x squared, but I factored the negative sign outside here. And that is the answer. Or if you've gotten something equivalent, that's also fine. That is part 1. Now part 2 is quite straightforward. We just need to verify. Right? We're given two curves. We need to verify that they meet at the coordinate x equals to half. So what you can do is write out the two equations, substitute x equals to half into both of them, make sure you get the same y coordinates on both sides, There, you have verified that these two curves will meet at x equals to half. Okay, now on to part 3. Applications of integration. We want to find the region bounded by the two curves and the y-axis. So you will have to use a GC for this. Yeah, so if you plot it out on your GC, it looks like this. It's the region between the blue, the red, and the y-axis. If that's not clear, I've reproduced the diagram over here. Okay, only that it's not red and blue. I use green and white. So the region that we're looking at is over here. Okay, so to get this region, by the way, we know that since you're looking at the y-axis, we're going to integrate from 0 to half. Remember, we verified the curves meet at x equals to half earlier on. Very convenient. So I want the integral from 0 to half of the green graph minus the integral from 0 to half of the white graph. So green minus white. So that is what we need to do. The area required is integral from 0 to half of the green graph minus 0 to half of the white graph. Now for the white graph, we already done it in part 1, right? So I just need to take the answer from part 1 without the plus c, of course. Okay, stick it inside here, evaluate from 0 to half. Now for this one, the green one, you should recognize that this is a standard integral under MF26. In fact, it is sine inverse, basically. Okay, but before I can turn it into sine inverse, I need to make sure the coefficient of my x squared is 1. So I'm going to factor out a 4, or rather a square root 4, which is 2. So you see my 2 over here, yes? So I also need to divide this by 4. So this becomes 49 over 4, which is 7 over 2 squared. So I have my a squared minus x squared. Perfect. Next, I'm going to move the half outside here, outside of the integral. So this is 1 over square root of a squared minus x squared. And that will give me sine inverse x over a. My a is 7 over 2, so 1 over a will be 2 over 7. So sine inverse 2x over 7. Don't forget the half that we have over here. Okay, and the rest of this is just this one. Right, we can evaluate this whole thing from 0 to half. Now, if you do that, I will spare you the details, right? And this is the final answer. Yeah, we're required to find the exact area, so you cannot use the GC. Right? If they don't mention exact area, just key into GC, press equal, and then that's it. Give it to 3SF. I hope this has been helpful, and I'll see you in the next video.